Okay. Good morning.
Good morning.
How are you doing? Ready for Wednesday midterm?
It's Monday.
It's Monday, so ready for Wednesday. That's right. Those are the main things that might come up in the exam. I just wrote that list. Okay. So the fine print is that even if it doesn't show up here, there could be a question on that. Maybe not. There's not going to be that much time, so we're probably going to focus on the main types of questions for this material. But there's no guarantee that just because something doesn't show up, then it's not in the exam. Okay. Okay. So let's walk over this list. So the exam has basically two chapters. So this is chapter 1, chapter 2. That's the stuff we covered up to today. So chapter 1 is essentially a review of functions, right? And the idea is to understand what a function is and what you can do with it. And you're going to notice that every time that we talk about something for this exam, there's going to be two versions of it. There's going to be the algebraic version and the graphical version. Why is that? Because if you remember, functions can be represented in many different ways. We talked about 4 ways to represent a function. 2 of them were sort of like warm-up ways to do it. And the 2 ways that we're actually going to be using all the time are which ones? Graphs and formulas, right? So you can draw the graph of the function on a Cartesian plane, or you can write the formula, f of x equal to so and so much. So either way, you should be able to see in either one of these 2 ways of representing a function, you should be able to understand the concept of continuity, of limits, of domains, of derivatives, and so on and so forth. Okay, so as you can see, every one of these topics, I wrote an intuition, and that intuition should be both algebraic and geometric. Okay, so I think that's a great way for you to practice for the exam, is to understand in those 2 ways every one of these concepts. So let's start with functions. What's a function? We talked about this before. Does anybody want to tell me in their own words what a function is? Maybe somebody who has not talked in the past. Yes, sir. Sorry? A machine. A machine, okay. It's a machine that eats one number and spits out another number, right? So you can represent this machine in multiple ways, but one way to do it is to draw a graph. And on the x-axis you put the input, on the y-axis you put the output. Right? So for example, if at x equals 1, y equals 5, that means that f of 1 is equal to 5. It takes the number 1 and outputs the number 5. Okay? Great. So what can we do with functions? Well, we can represent all kinds of transformations that can represent problems from real life, like optimization problems. There's going to be all kinds of applications of it. For now, we're taking them as an abstract object, and we're trying to understand them as much as possible. So one thing we can do with functions is we can figure out the domain, first of all. What is the domain of a function?
All possibility of x.
Okay. Basically, you said all possibilities for x, and that's correct. Basically, you look at the formula, in the case of an algebraic expression, and you ask yourself, what are all the values of x that make sense to plug in there? What are all the values that give me some expression, something that I can calculate? For example, something that I cannot calculate, at least in this course, is square root of minus 5. Okay? At least in a real mathematics course, this thing does not exist, so minus 5 is not in the domain of the function square root of x. Okay? Another thing that cannot exist is if I have an expression that's a fraction and has a 0 on the bottom. So if you have a fraction, for example, x divided by x minus 5, and you said x equal to 5, then the bottom is equal to 0, which does not make sense, and therefore 5 is not in the domain. Okay? So that's algebraically. Graphically, you can easily see the domain because every point that is on the graph has a corresponding x value. Those are the points in the domain. If an x value does not have any point on the graph, that means that x is not in the domain. For example, 1 over x, right? 1 over x looks like two curves like this, but it actually doesn't have any point for x equals 0. At x equals 0, there is no value for the function. You can see that graphically. So x equals 0 is not part of the domain. Okay, now having a function f, you can construct other functions based on that function f. For example, I can take a function and I can move it up or down, right, to get another function that's very similar, right? I can move it to the right side and to the left side, and I can stretch it vertically and horizontally. Okay? So by now you should be able to figure out how to do this algebraically. For example, how do I stretch a function by 5 vertically? How do I do that? Multiply by 5, right? Multiply the entire function or inside? The entire function. I take the function, whatever expression that is, multiply by 5, and the whole thing gets stretched by 5. If I wanted to move the function, let's say to the right by 5, I have a function f of x, and I want to move the whole thing to the right by 5. Okay, I have to subtract 5, okay, but not outside the function. It's not f of x minus 5. It's not f of x minus 5, but f of x minus 5. Okay? In other words, I replace every appearance of x, whether it's just 1, 2, 3, or 4 x's that show up in the equation, I replace them all by x minus 5, x minus 5, x minus 5, and the whole thing gets magically shifted to the right by 5. Well, okay, not magically, right? We talked about it. We talked about why it gets shifted to the right when I write x minus 5. When you would think it gets shifted to the left, but actually it's to the right. Okay? However, if I say f of x minus 5, then the whole thing gets shifted down by 5. That's right. That's right. Okay, so those are transformations. Then we talked about inverse functions. Okay, so again, inverse functions are functions, so they're machines, right? They have the property that if x transforms, for example, 1 to 5, then the inverse function transforms 5 to 1. In other words, the inverse function undoes what the function did, right? For example, the function e to the x and the function logarithm of x, natural log, are inverse functions of each other. So if you take x, you take the logarithm of x, and then you take e to the x, and then you take e to the that, you get back to x. Okay? If you take a number, you take the logarithm, and then you take e to the that, you get back x. If you take a number, you take e to the x, and then you take logarithm of that, you go back to x once again. Okay, so you can cancel them out with each other. Now, graphically, how does the inverse function look like compared with the original function? Okay, it's symmetric with respect to y equal x. What does that mean? You draw the graph of the function. You draw the line y equals x, which is a diagonal line, right? The function y equals x is a diagonal. And then you reflect the function around that axis. Okay, you flip it using, as axis of symmetry, the diagonal line. And there you go. That's going to be the result of that is f minus 1. That's graphically. Now, algebraically, how do you find the inverse of a function? Maybe somebody who has not spoken yet. Or, yes, sir?
We switch the y and the x, like we switch the places.
Okay. So you take the expression f of x equals whatever it is. Maybe we should do it. I don't know. Let's do an example of this. Let's see. So find f minus 1 of x, and f of x is equal to, I don't know, let's say square root of 7x plus 1 minus 4. Okay, that's a 4. Okay, so what do you do? Well, you can think of this as y equals square root of 7x plus 1 minus 4. So the first step, if you prefer to do it that way, the first step would be to write x equals square root of 7y plus 1 minus 4. In other words, to replace the value of x and y, to flip them, essentially to change the values of x and y. Why do we do that? Why do you think we do that? Sorry? Because the domain and the range should switch. Yes, I think that's one way to put it. The way that I would describe it is we're used to using x as the input variable. X is what comes in, y is what comes out. But guess what? We're changing that, and now we're allowing y to be the input and x to be the output. Right? So now we change them so that the input becomes the output and the output becomes the input. Okay. And then the second step is to solve for y. Okay, we want to get y equals something. So we write x minus 4 is equal to square root of 7. What? Oh. Oh, sorry, plus. Yes, thank you. Thank you, sorry. You're paying attention. Okay, now we take squares on both sides and we get x plus 4 squared is equal to 7 y plus 1. And then we subtract 1 and we divide by 7 and we get x plus 4 squared minus 1. The whole thing divided by 7 is equal to y, and that is equal to f minus 1 of x. So there you go. That's the way to find inverses. Questions? No questions. Okay. At this point, it should be true, if we did this correctly, it should be true that f of f minus 1 of x is equal to x. And this is an algebraic problem that one should be able to do it. It will be a bit of a mess, but it should be true that if I plug this in here, and if I write, square root of 7 times this plus 1 minus 4 should be equal to y. Should be equal to x. And it also should be true that f minus 1 of f of x is equal to x. Now, is this f minus 1 of x, is that the same thing as 1 over f of x? Because it's a minus 1, right? But it's not the same, right? It's an abuse of notation, or it's a different notation. It's the same notation used for something else. Okay, great. Let's go back to a review. Okay, so what was the next topic in functions? We talked about piecewise defined functions. Okay, so I want everybody to be familiar with piecewise defined functions because, especially in the next couple of sections, for example, continuity, there's too many continuous functions. We said there's a zoo of continuous functions. All the functions you've heard about, practically all of them, actually all of them, are continuous on their domain. Exponentials, trigonometric functions, including the tangent function, polynomials, and so on and so forth. What happens with the tangent function? The tangent function looks like this, with some funny looking s's, and they're definitely separate. What about the function 1 over x? There's definitely two separate lines. So why is that a continuous function?
Because you limit its domain.
Because we're only talking about continuity wherever the function is defined. So it makes sense to talk about the continuity at 0 because the function is not defined at 0. The function 1 over x is not defined at 0. So that seems like a technicality, but that means that we can say all these elementary functions, trig functions, logarithms, exponentials, polynomials, even rational functions, all these functions are continuous. If we want to come up with some function that's not continuous, we have to go beyond this zoo of functions. And that's where we start talking about piecewise defined functions. So there's a good guess that these functions are going to come up somewhere in the exam. That's why I want you guys to be very familiar with piecewise defined functions and to understand how to draw them and what they mean. Okay? All right. And You guys know how they're defined, right? You know what? We're going to do an example in a moment, so let's just keep that in mind. Okay, let's go to the next section is limits. Okay, so you should understand this is probably the key concept for this first midterm, even if there's other ideas that may be more important, like derivatives and continuity. They're all defined in terms of this one concept of limits. So what does it mean when if I write that, let's say, limit of f of x when x tends to 2 is equal to 4. What does that mean? Can anybody maybe tell me what that means in the wrong words? Yes, sir. Okay, very good. So let me, you said as x approaches 2, y approaches, or the y value, the y-axis goes to, the y-axis values go to 4. So let me not draw it to scale. I'm going to put 2 here and I'm going to put 4 there. What it means is that whatever the function is doing, I don't know what the function looks like, but I do know that as the values of x approach 2, the values of y approach 4. Okay, does that limit, even though I drew a hole at the point, does that limit equal to 4? Yes. Yes, actually. As it turns out, and this is one of the things to learn about limits, is that it doesn't matter what the function is doing at x equals 2. It only matters what the function is doing around 2. And you can see that as the function, if you look at values of x that are close to 2, the values of f of x become very, very close to 4. That's what it means. Whether there is a point here or not, and I could even have a function that is defined at 2 to be equal to 10. It doesn't matter. The limit is still existing, and it's still equal to 4. Okay? So I want to stress this, that it does not have anything to do, this value of the limit does have nothing to do with the value of the function at the point. Okay? I know you guys or I imagine you guys are fond of plugging in x equals 2 in there. Sometimes it works when the function is continuous, because at that point, that's the whole point. The limit is equal to f of 2. But in general, that's not necessarily the case. Okay, that's what a limit means. That's what it means. It means a statement, as x approaches 2, f of x approaches 4. Okay, now, there's a bunch of properties about limits. Let's go back to the review page. There are what we can call vertical and horizontal asymptotes. Vertical and horizontal asymptotes are exactly what they sound like. You draw a dotted horizontal line, and the function is supposed to approach that horizontal line as x becomes larger and larger. The Greek etymology says that it's not supposed to touch it. In fact, it can touch it. It's okay. It's just supposed to get closer and closer. Yeah, it can touch it. Manriquez is saying that he blew his mind. Let's see. So, you're Manriquez, right? You're Manriquez, right? Is that? Oh, what's your last name?
Mies.
Oh, your last name is Mies?
Yeah.
Where's Manriquez? Oh, sorry. Mies. All right, so you got a horizontal asymptote. You got this horizontal line. And the idea, let's say that this is, once again, this is 4. Here we will say that the limit when x goes to infinity of f of x is equal to 4. What does that mean? It means that as x becomes larger and larger, the values f of x become closer and closer to 4. In other words, they become closer and closer to this line. Can they touch it? Well, according to the Greeks, they're not supposed to touch, but in fact they can. You can have something like this. As long as they become closer and closer and closer, you can touch it as many times as you want. You can cross as many times as you want. The big deal of this definition is that they're supposed to get closer and closer and closer. Okay? In general, okay, fine. In general, you're going to see more something like not really touching, but just getting closer and closer. But it doesn't. That's not the important part of the idea. Is that as x becomes larger and larger, f of x becomes closer and closer to 4. Okay. So here's the graphical intuition. The algebraic intuition should also be very clear. For example, the limit when x goes to infinity of, well, you know what? Let's do a non-trivial problem. For example, let's do e to the x minus x squared as x goes to infinity. And this is also going to illustrate what happens with the other concepts of limits. You know, these other things that we wrote about limits, that I wrote about limits. So how do you calculate limits? That's the other concept. For example, we have the limit rules, okay? And we have multiplication by conjugates. I wrote that explicitly there because I think it's a very commonly used trick that you all should be familiar with. Multiplication by conjugates allows you to modify or to rephrase a limit so that you can actually compute it. But why would you even want to rephrase it? Why not just plug in, or why not just evaluate it? Well, as it turns out, there are something called the limit rules that come with their own fine print. And the limit rules say something like this. If you have two functions, f and g, let's say, and they both have a limit at x equals 2, for example, they have a limit as x approaches 2, then the sum of those, the limit of the function f plus g is equal to the limit of the function f plus the limit of the function g. In other words, if you have the limit of a sum, you can break it down into two simpler limits. Okay? That's the first rule. The second rule is very similar with minus. There's a third rule. If I have a quotient of f divided by g, then the limit of that is equal to the limit of the top divided by the limit of the bottom. But then the fine print becomes important. The limit of the bottom cannot be 0. That's right. As long as the bottom converges to something non-zero and the top converges to whatever, you can take the limit of the fraction of the limits. In other words, break down the fraction into two limits and calculate that. These rules are designed to simplify your limit, to make it into a piecemeal problem, to a simpler and simpler problem, until you can say, okay, that limit has to be equal to whatever, 5, and then you can go back and do the algebra and calculate the rest of the limit. For example, in this case, this looks like a complicated problem. I mean, I don't know what e to the something converges to when x goes to infinity. I don't know that. But I know, because of the rules for limits and for continuity, that this is equal to, okay? I'm going to jump ahead to continuity because, I mean, might as well. We're already in the middle of the review. When a function is continuous, for example, the function e to the x is a function that's continuous, then you can bring the limit inside of the function. So this is equal to e to the limit when x goes to infinity of x minus x squared. Okay, that's a powerful trick to figure out values of limits. Okay, now, by the way, okay. This is also not an obvious limit. What happens with x minus x squared as x goes to to infinity? That goes to negative infinity. Why does this top part go to negative infinity? Sorry? Yeah, we could divide by.
No, because you check which one's the higher degree of the function.
Yeah, and then divide by. Yeah, except that this is not really a fraction. I mean, we could rewrite it as a fraction, but I think it's a little bit easier in this case. So we have something that goes to infinity, x, and we have something that goes to minus infinity, or to infinity also, x squared. And so this is infinity minus infinity. Okay? So you have a case where something goes to infinity minus something that goes to infinity, then what? Well, in principle, you don't know. It could be anything, right? So we have to rephrase. In this case, we rephrase by, my suggestion would be to just factor out. Limits when x goes to infinity of x times x minus 1. 1 minus x. Let me just write it again. Sorry. E to the limit x to infinity of x times 1 minus x. Okay, now what happens? Now we have a product of two things. This one goes to infinity, and this one goes to minus infinity. Okay, so the product of the two goes to minus infinity, right? No problem with that. So as the top part goes to minus infinity, okay, then e to the minus infinity is what? Is 0, right? Think about the function e to the x, and think about what that function looks like for x becoming, I don't know, minus 100, minus 1,000, very big and negative. What does e to the x do to that number that is very big and negative? It goes to 0, right? Okay, so this is equal to e to the minus infinity, if you will. That's equal to 0. Yes?
You know, on your first step, you took the limit as x go to infinity and you applied it to the exponent.
Yes.
Does that only work when your base is a constant?
A continuous function. Any continuous function. So the question is, this trick of bringing the limit inside of the function, the question is whether it only works when this is a constant. Well, I mean, anytime that you have a continuous function, you know, and such as e to the x, you can bring the limit inside of the function. Okay? You may need to be a little bit careful. This idea of e to the minus infinity is not really well defined. You cannot really evaluate e at minus infinity. But really what I mean by this is that as this thing becomes more and more large and negative, e to the that becomes smaller and smaller and smaller, so the whole thing goes to 0. Okay? And this is what kind of asymptote? Is it a vertical asymptote?
Horizontal.
It's a horizontal asymptote. That's right. We just showed that this function, whatever it may look like, has a horizontal asymptote at 0. Okay? Great. Okay, so what else? So calculation of limits, so limit rules and conjugates. I just mentioned the limit rules. Conjugates, multiplication by conjugate is a way to rephrase the limit so that you can actually compute it. Otherwise, you might get stuck with something that goes to 0 divided by something that goes to 0. We've done several examples of those, so maybe if you want, we can do one, but I'd say let's move on because we have still a bunch of stuff to cover. And we can start talking about continuity. Okay? Questions about limits? Any other question about limits? Yes?
Could you have
Miss.
taken the higher degree in limit of x minus x of 2 and then plugged it in since x squared is increasing faster than x?
Wait, say that again.
In the next one over.
Yes?
Couldn't you just have taken the higher degree of minus x squared
And multiplied up and down by?
and just plug an infinity into that?
Okay, if you plug in infinity in here, you get infinity minus infinity. And that is an undefined undefined expression.
Would it be acceptable on a test to ignore x? Because it is, once x approaches such a high number, x becomes insignificant.
But you have to show that. So Mises' point is that as x becomes really, really large, x becomes insignificant compared with x squared. So therefore, you can ignore it. Okay? And the answer is, in principle, yes, but I don't like this idea of ignoring it because it basically just means that you're supposed to trust the grader that you know the answer so well that you can ignore it. And if I'm just reading what you're writing, it may be that you know it so well that it's obvious to you, or it may be that you're guessing, or you don't really know what you're doing. So in exam, you really need to show why it's true, not just that you know so much that you should write the answer. Okay? That's a good question, by the way, and that's a good principle to have in general. Even if you're very good and you know all this material, you have to get that across to the person that's grading the exam. Sometimes the person that's grading the exam is only going to be grading one question at a time. They're going to read your question and going to go move on to somebody else. So you don't get to prove yourself with some other question showing that you're very smart. What you need to do is in every question, you need to show that you know the answer without just guessing the answer, but you need to show your every step. Okay? Great. Thanks for pointing that out, or thanks for asking. Any other questions about limits?
I have a question.
Yes.
So you know how we can take the derivative using the limit way, but if we know how to take it the other way on the exam, do you want us to show it?
Okay, that's a very good question. I was imagining that this question will come up because we have learned in the past couple of lectures, we have learned to calculate derivatives, and it's hard, right? I mean, there's like a whole procedure to it. You have to calculate some big complicated limit, right? And then in the end, you get something out that you may already know because you know these formulas for calculating derivatives, okay? So, Wendy, right? You know,
So that last time too, it's Mary.
oh, okay. But where is Wendy? Wendy, do you also want to know the answer to that question? No, I'm kidding. So, Maria, Marisol, sorry, Mary, okay, fine. So, Mary, that's a very good question. And after this exam, we will learn those rules and you'll be able to use them as much as you want. For this particular exam, I want to make sure that you understand not the formula to just plug in and then you get the derivative out, but that you actually understand how, what the derivative means and how you would compute it if you didn't know these formulas, okay? So one way to do it, and you'll see this maybe in the sample midterm, is we're not going to ask you, but we're not going to ask you necessarily, here's a function, calculate the derivative. But we may ask you something like, here's a limit, find out what function this is a derivative of, and calculate the limit, okay? So if you don't know the function, if you don't know what you're doing with limits, you're not going to be able to answer that question, even if you know all the formulas for limits from previous math courses. Okay? Yes, another question? I saw somebody else raising their hand. No? Okay, all right. Okay, so all right, so are we already here? Continuity? Sure, let's talk about continuity. So, a function is continuous when what? What does it mean for a function to be continuous? Let's say, what is the graphical intuition behind continuity? Yes, Dimitri? Are you Dimitri? No. Ah, you're not Dimitri. Okay. Where's Dimitri?
You're over 3 so far.
Yeah, it's 250 of you, right? It's hard. Okay, sir, what's your name? Tolu. Did you already give me your student bio? Okay. No. Okay. Okay. Tolu. Yes.
It's how you could draw the entire graph without lifting up a pen.
That's correct. That's correct. Tolu is saying a function is continuous when you can draw the graph of the function without lifting your pen. That's exactly right. That's the idea of a continuous function. For example, the function absolute value of x, right? It looks like a v. And you can perfectly draw this function with a v, even though the function has a corner. That's okay. The function is continuous, so you can actually draw it without lifting the pen, no problem. Is the function absolute value of x differentiable at 0?
No.
It's not differentiable, but it's continuous. Okay. Yes.
Yeah, you said earlier that also if it has a point undefined, it can still be continuous, such as 1 over x.
Yes. Oh, I see. So 1 over x you cannot draw without lifting the pen. Okay, fine. That's a good point. The thing is, 1 over x is not defined at 0. So I guess that the intuition works when you have a function defined on the whole interval. If the function is not defined at some point in the interval, then you're going to have to lift your pen. That's true. Okay?
So long as it's defined in the interval, it's continuous.
Yes, as long as it's defined on the whole interval, you say that it's continuous in the interval if you can draw it without lifting your pen. Okay? That's a more precise way to write it, right? So because Mrs. point is that the function 1 over x actually cannot be drawn without lifting the pen. And what I was saying is that function is not defined at 0. That's what's happening with that function. Okay, so technically, if you wrote this as an expression, as a formula, what does it mean for a function to be continuous? Well, what it means is that okay, so continuity is written in the following formula. That the limit of f of x when x goes to, let's say, a, is equal to f of a. So in that case, if we looked at the function that we talked about before, for example, this function right here, this function is actually not continuous at 2. It has a limit. It is defined at 2, no problem. But the limit and the function defined at 2 and the value at 2 are different. Okay? So the only way that that function can be continuous at a is if the value of the function is equal to the limit. Okay, so if I give you a piecewise defined function and I ask you if the function is defined, is continuous at a point, you need to compute two things. You need to compute the limit of the function when x goes towards that point, and you need to compute the function evaluated at that point. And those two things should be the same. Okay? Let me give you an example of that. Let's see. So, example. Suppose that f of x is equal to square root of minus x when x is less than 0. It's 3 minus x when 0 is less or equal than x less than 3. And it's x minus 3 squared when x is bigger than 3. Okay. So the question is, where is f continuous? In other words, find the points x at which the function f is continuous. So we're going to do this graphically. I think it's the easiest way to solve this problem. And for that, you need to basically graph the function. So this is a piecewise defined function. We were saying they're probably going to be important in the exam because every one of these functions by themselves is continuous everywhere they're defined. So that's not very interesting. But once you have piecewise defined functions, things can become more interesting. So, for example, square root of minus x when x goes to 0 looks something like this. Do you agree? Great. Now, should I include the point x equals 0 in there? In other words, should I? No. Okay, this is only for x less than 0. At 0, the function is this expression is not saying anything about the function. So I'm going to write an empty circle in there to indicate that that line does not actually touch x equals 0. Okay, this is true for every point less than 0, but not at 0. Okay, now we have the function 3 minus x. So let's say that this is 3, this is 3. How does the function 3 minus x look like? It's a straight line that looks like this. Right? Anywhere between 0 and 3. Okay, does it include 0?
Yes.
Yes. So that means that I can draw a full ball in there. Does it include 3?
No.
It does not include 3. So we draw an empty ball in there, indicating that as far as this definition is concerned, the function is not, this line does not go all the way to 3. Okay, what about x minus 3 squared? Let's think about the function x minus 3 squared. Can anybody tell me what the function looks like? Compared with the function x squared, for example. Yes, ma'am. It looks like the function x squared. Okay, but more exactly.
When x equal to 0, when x equal to 3, the y.
Okay, good.
X square, function x square, and switch this function to y.
Okay, that's right. So it looks like the function x squared, but it has been shifted to the right by 3, right? Great. So that means that it looks like this, more or less. Okay. So let's see. So, for example, at the point x equal to -1, is the function continuous? What do you think? It looks continuous. How do you argue conclusively that this function is continuous at -1?
Well, x minus 1 is defined its domain.
Okay. First of all, the -1 is part of the domain. That's good. That's important.
Minus 1 also is the limit of this function. This limit exists.
Okay, the limit exists at -1. When x equals -1, the limit of the function exists. How do we know that?
Because as it approaches it from the positive and negative side, the one-sided functions are the same, making the limit at that point also the same.
Okay, Mies is saying when the limit exists because when x converges to -1, the value of the function converges to something. You can see it in the graph, but we would like something a little bit more precise. I mean, you're essentially rephrasing the statement, right? The limit exists because as x approaches -1, f of x converges to something, right? So, as a matter of fact, we already know some strong results about continuous functions. Remember when we said that there's a whole zoo of continuous functions? All these functions, square roots, trig functions, logarithms, exponentials, all these functions are continuous wherever they're defined. Okay? So in particular, this function that you see right here, this function is one of such functions. Okay? So it is continuous wherever it's defined. Right? That means that if I forget about what happens everywhere else, if I just look at this piece over here, this piece is continuous because the function square root of -x, which is defined anywhere for negative x, is a continuous function. Maybe that function is not the best example, but let's take the point x equals 1. Okay? This function, the function 3 minus x, is continuous. Do you agree? If you just look at the function 3 minus x, is a continuous function. Okay, when we're asking about the continuity of this piecewise defined function at 1, we can essentially ignore what happens over on this side and over on that side and just focus on this piece right here. And we know that the function 3 minus x is continuous, so it must also be true that this function is continuous at x equals 1. Okay? So by what we learned about continuity, because continuity only involves what happens in the vicinity of the function, we can ignore what happens with the function here and with the function here, and we can say with certainty that this function is actually continuous at 1. How do you write that in an exam? Well, you say something like, because the function 3 minus x is continuous everywhere, right? The function f of x that I'm defining right on the piece of paper is continuous between 0 and 3. Okay? Not including 0 and not including 3. Great. That's what you would say. So now, what happens at 0? Oh, by the way, the same thing can be said at every other point other than 0 and 3. At every point different from 0 and 3, we have a function that locally looks like a function that's continuous, and therefore, f is continuous at that point. It's the same argument. So, at x different from 3 or 0, f of x is, sorry, at a different from 3 and 0, f of x is locally identical to a continuous function as x approaches a. Therefore, f is continuous at a. Okay? This is a slightly subtle argument, but you should understand why it works. And that means that the function is continuous everywhere except not necessarily at 0 and 3, but everywhere else, for sure it's continuous. Okay, what happens at 0 and at 3? So a equals 0. Is the function continuous? It's not continuous. Why not?
Because it's equal pen.
You can see it in the graph. You have to lift the pen. That's right. You have to lift the pen. So if you wanted to write this mathematically, I mean, in the graph it's obvious that it's not continuous. If you wanted to write this mathematically, you can say something like limit when x goes to 0 minus of f of x is equal to 0, and the limit when x tends to 0 plus of f of x is equal to 3. So the limit of f of x when x goes to 0 does not exist. Great. So not continuous at 0. What about, oh, we're running out of time. A equals 3. Is it continuous at 3?
No.
It's not continuous at 3 because it has a hole. 3 is not part of the domain. It looks like it would be continuous, but it's not continuous because the function is not defined at 3. Okay, sorry for running over. I'm going to send you an email telling you about the place for the meeting tomorrow, and we'll take it from there.